It's nice to have this opportunity to do this talk, and it's going to be on iterative circle projections. This is a project based around some fairly elementary geometry. It does touch a bit with other more interesting concepts like polarity and projective geometry. But essentially, it's a fairly interesting system that's based on some very elementary ideas. So here's the system. We have a ground line, just a line, and we have a circle, and the line doesn't pass through the circle. And on this circle, we begin with 2 points. We call those x1 and x2. And we're going to generate more points around the circle by a kind of iterative process. So how does this process work? Well, in general, we'll have a lot of points, x1, x2, x3, all the way up to xn. And I'll tell you how to generate point x plus n plus 1 in terms of the previous 2 points, xn and xn minus 1. So here's how it goes. The first step is that you draw a tangent line to xn, in this case n is 2, and you find out the point where that tangent line meets the ground line. I'll call that G2 in this diagram. Second stage of the process is to draw a line back up from G2 towards x1, or in general, drawing this line from the place on the ground to the point xn minus 1, the second to last point generated so far. And you'll notice that this line is actually, well, almost always going to intersect the circle at 2 points. And whenever it does that, we pick the point on the circle which lies on the line and is not equal to x1, or not equal to xn minus 1, to become the new point. So if I just repeat this a few more times, you should get the idea. So draw the tangent to the latest point in the sequence. Look where it hits the ground. Draw a line back to the second latest point in the sequence. And find the additional place of on the circle that line back intersects is at. And that's going to be the new most far on point in this sequence. So we carry on. Tangent and back to the second to last one. So basically, our setup is kind of like this. What are the inputs? Well, the inputs are the positions of those 2 points around the circle, and also the height that this circle has above this ground line. Given that information, we're interested in what kind of dynamics this kind of system has. How is it that these systems will move around? So anyway, we can use these yellow arrows here to denote the order in which these points are generated. That'll allow us to do away with our labels. And so we can see that the next point generated, just draw this red tangent line down, draw this green line back up, which skewers 2 points, and look at the new point it creates, and so on and so forth. And then we might ask, well, what happens if we change the initial conditions? We are interested in how the initial conditions change this setup. Well, you actually get some quite nice movies of these kind of things happening. Because by shifting these initial conditions, all the other parts of this system move continuously. However, in this case, if we just shift this around a bit, we can see that from certain initial conditions, we actually end up with a 4 cycle. Now, when I refer to cycles, what I mean is like an n cycle or k cycle would be when this sequence of points generated repeats every k steps. So this is a for cycle. And we might be interested in how to find things like this. So one way I firstly approach this problem is via using Cartesian coordinates. And so I wanted to try and get algebraic expressions for all these ways that the circle is bouncing around. Now it turns out that, as often is the case, the old sine, cosine and theta way of parameterizing a circle is quite hard to work with. And so this more kind of ancient technique of doing a parameterization of the circle using this kind of, well, it's almost like a 2D stereographic projection. This kind of method turns out quite well. So what we do here, we have a fixed point at 0, -1, and we have a variable point on this horizontal line. So as t varies, this point slides backwards and forwards. And then we look at the place where this line between 0 and -1 goes through t1, and it's going to intersect the circle somewhere, and it can be shown that the coordinates that happens in Cartesian space are given by this equation here. And this is quite nice because it gives us a new way to sort of parameterize the circle. You can see that as t goes from infinity to -infinity, it's going to rotate this stick all the way around and give us all the points on the circle, except perhaps 0, -1. That's kind of a limiting case. So how does this help us with our problem? Well, basically, we can find values of t according to this equation, which tell us what our points are. So we can find a Tn such that xn is equal to c of Tn, and so forth. And by doing a bit of geometry and things, we can work out what t of n plus 1 is in terms of the subsequent two parameters, Tn and Tn minus 1, and also the height h that the centre of the circle is above the ground. So what we're essentially doing here is using this setup, which allows us to essentially describe where the points on the circle are according to this 1D parameter t. And now all we have to do is follow how these t's change, and they do so according to this fairly simple difference equation. And so this can be written as is shown here. Basically, we can think of the change happening where before we have the pair of, well, parameters for the circle points, Tn minus 1 and t of n. And then on the next time step, we're thinking about points t of n and t of n plus 1. And they will have values like this. So using this now, we can iterate our systems and explore them kind of algebraically. And by doing that, so by using these equations then, we can have a look at some of the different periodic orbits just by solving those equations for periodic solutions. So here's a 2 orbit that I found. Here's a picture of a 3 orbit. And here's a 4 orbit. And so we have this, but the thing is, all of these are just special cases, and you can solve those equations I was looking at precisely to find all of the different 2 orbits and such if you set h to be a specific value, like say 2. Then you can do all the things you need to, but more generally it's quite a lot more challenging. So in general, it's it's perhaps preferable to try and find a different approach. So one bag of tools which is really useful here, and I think this is really the main thrust of my talk, because these systems I'm studying, I'm only about halfway through this project, but I think these tools are actually really quite useful. And it's these ideas of poles and polarity which go back to antiquity, I think. And surprisingly, they're not taught much more in schools these days, at least where I went. And that's a shame, because I think these are some very beautiful mathematical ideas. So, okay, this is sort of pure theory. So suppose we have a point which is outside of some conic. Just for simplicity, we'll use a circle as our conic. So we have this point, big P. Now, if we want to find the so-called polar of big P, what do? Well, a polar is a line which is associated to a point. So in this theory of polarity, because of the presence of this circle, every line can be associated to a point, and every point can be associated with a line as bijections. So these are called these sort of polar relationships. So the polar of this point is this associated line, and how is it defined? Well, it's defined as the line that goes through it can be defined as the line that goes through the two spots where tangent lines to P meet this conic, zeta. So to find the polar, draw these two tangents from P to the polar, and then where they meet you get your polar line. Now, I'm only going through this quickly, so I'll just tell you a couple of very important facts about these things. One of them is, so you'll notice I'm using this notation, pperp. So I'm using capital letters for points, smaller case letters for lines, and the line is equal to the point perpendicularized, or polared, or the dual of it. And it's got lots of different names. So anyway, just as every point has an associated polar, every line has an associated pole. And in fact, the pole of a line is just the point that's polar is that line. So if you like, it's kind of like doing the inverse operation. If you think of this kind of perpendicularity thing as something that maps points to their polars. So the most important quality that these pole-pole relationships have is this very, very important one here, which says that if we have a point P and a line Q, well, P is going to touch Q if and only if the perp of P touches the perp of Q. So the perp of this point P is going to be this line, this polar line P perp, and the perpendicular and the perp of this line Q, that's going to be the pole Q perp. So the first two touch each other if and only if the second two touch each other. So this kind of doing this kind of polarity operation, this kind of mapping on everything, doesn't interrupt any, well, it kind of preserves incidence and non-incidence amongst objects. So given all this, we can work out what the pole is that generates a polar line inside the circle. How do we do it? Well, basically, if we just put one point, well, if we just draw one point P and one point Q that are actually outside of, they're on this line going through a circle, but actually outside of it. Well, what we can do then is we can take the polars of those 2 points, and it turns out then that the spot that those 2 polars meet is actually going to be the pole of our original line, and it doesn't matter where we put big Q and big P for this to work. So this is already quite a interesting observation. And another thing we might ask is, how do we work out the polar of a point which is inside the circle? Well, actually there's a very similar kind of solution. If we draw these lines P and Q and R through this point, and then we work out what their poles are, joining those poles will give us the polar line of P. So these are pretty important ideas, although I should just mention that actually there is a method which you can probably derive from all this if you thought about it for long enough, but there's a way of actually working out what the polar of a point is without having to meet the tangents of the circle. So in fact, if you're already given the circle or the conic, you can calculate poles and polars completely using straight edge constructions. That means that they are purely belonging to projective geometry, the geometry of only the straight edge, as opposed to Euclidean geometry, which also requires a compass. So projective geometry is kind of more basic, and so are these constructions. So how does all this help us with our circle problem? Well, firstly, it's important to note that it can be described in terms of this language. Here's our point xn. Well, the line which is the tangent to xn is just actually the pole of a point xn. This red line is called xn perp. And it meets the green line here. And then if we draw another line from that point up to xn minus 1, well, we can give that point a name. It's where xn perp meets this line G, the ground line. And then we have a name for this blue line here, because this blue line is just joining this subsequently membered ground line point with this point xn minus 1. And we see that these 2 points, xn minus 1 and more importantly xn plus 1, are just the 2 points where this line intersects with the circle. So basically we're able to describe our next point in terms purely of straight line construction based methods. So we can also use this kind of language now. Since we can use it to describe the process, we can also use it to describe the actual orbit systems. So if you ask the question, well, I have a general circle, a general height above my ground line, how do I work out what all of the different period 2 orbits are? Well, here's how you do it. Just put a variable point P on this ground line, and it doesn't matter where you put it. If you take the polar of that ground line, that'll be a line which cuts through these gold arrows, and the place where that line intersects these 2 circle points gives us x1 and x2, the points on our 2 cycle. Similarly, if you want a 4 cycle, you can do it like this. So if you put any generic point P down, and then if you take the polar of that, that'll be this blue diagonally upwards line. and that's going to be giving us points x2 and x4 on our cycle. And if we also look at where this blue line here, which is the polar of P, where that meets the ground, that gives us our other kind of foot. And if we take this other foot point, work out what its polar is, that gives us points x1 and x2, sorry, x1 and x3 on our 4 cycle. And the thing is with this method, not only does it give us all of the different cycles we need, not only is it independent of the height of the circle, but it only relies on straight edge construction. So rather than just being something that works on the Euclidean plane, this actually really belongs to projective geometry. And since it only uses straight edge constructions, it means that we could replace this setup with other conics, hyperbola, ellipses, whatever, and the same dynamics would still occur, and these would still be solutions because they're all pitched in this kind of projective geometry language of straight line constructions. So thank you very much for your attention.